right, as we begin today, I want to review some things we talked about yesterday. We got into algebra again at long last. We've done a lot of geometry stuff and probability stuff and statistics stuff and graphing stuff. It's just like, we're back in algebra again, and this is nice. And it was nice to have something a little bit more, straightforward, right? And yesterday we reviewed over what makes terms like to each other. Joshua, what make terms like to each other?
The bases. Well,
Lana, can you help me?
Like the same power?
Well,
the same power, but like...
Tell you what, let's try this. Josh, can you give me an example of two terms that are like to each other?
3y cubed and 4y cubed.
Okay, and why are these two like to each other?
Because of the y and the cube. They have the same variables.
They have the exact same variables, including the same quantity of variables, right? 3y cubed and 4y squared wouldn't be like, because although they both have y's, they don't have the same number of them, right? Can you give me an example of maybe a couple of more involved terms that are like to each other, Lana? Give me something a little more crazy.
Negative 24.
Have fun
A
here.
squared, C squared, Y squared.
Okay, now can you give me a term that would be like to negative 24, A squared, C squared, Y squared?
That's so weird. Negative 100, A squared, C squared, Y squared.
And again, as long as the letters, including their exponents, are exactly the same, the terms are like to each other, right? And we said if terms are like to each other, then we can add them. So if I were to add 3y cubed and 4y cubed, Joshua, we would get 7y cubed. Remember, when you add the terms, you're adding how many y cubes you're getting. So you just get 7y cubed. So we don't do anything weird with the letters. We leave them the same. So, Lana, if we were to add a negative 24, a squared, c squared, y squared, to a negative 100, a squared, c squared, y squared, what would we get?
Negative 124, A squared, C squared, Y squared.
Good, negative 124, a squared, c squared, y squared. Again, when you add like terms, you don't mess with the letters at all. We said that if you had an a cubed b, you couldn't add that to an a squared b to the fifth. They're not like to each other. But we said as long as you have matching bases, you can multiply. Really, even if there were a mismatched base, you could still multiply together. But you really only combine together like bases. And yesterday, class, we said that when you multiply like bases, you add the exponents. Good. Scott, I couldn't hear you. Let's try that again, class. When we multiply like bases, we
add the exponents.
Add the exponents. Good. Lonnie gave a little extra volume on Scott's behalf there. So when we add the exponents here, Joshua, what do we get as we multiply these together?
A to the fifth, B to the fifth. Wait, no, B to the sixth.
Good.
And C.
And there's this random little C that has no friends. Well, he doesn't combine with the other letters, but he's still in the mix, right? It's not that he doesn't exist, right? Like if Glenn has no friends, it doesn't mean Glenn doesn't exist. It just means he's lonely, right? Like this little C that has no friends to play with. It's just there, existing. I'm just thinking I'll do one. Questions on this? We also said that we could divide, but how do we generally show division in algebra, Lana? I don't usually use this little symbol here. What do I generally do?
A fraction.
I'll use a fraction bar, right? So if I wanted to have, say, an a cubed, b squared, c to the fifth, divided by, say, an a, b squared, c to the seventh, d, or something like this. They don't have to be like terms to divide them, but we only actually combine as we divide like bases. And we said that when we divide like bases, class, we subtract the exponents. Essentially like we cancel away matching parts and leave the winner where he is. So as we look at just the a's, as we divide this, Lana, we're going to get
A to the second.
a to the second power when we subtract. Now, Lana, I've got to choose though. Do we put the a squared in the top or in the bottom?
I don't think you put
Joshua, can you help us? It would be the top. Because in a sense, Lana, there's 3 a's here, 1 here. Well, they each lose a guy. But the 2 left over are in the top, not in the bottom. The a is gone as it cancels with 1 of these three. So we said the a squared would be left here. Lana, here I've got a b squared and another b squared. Well, they're exact matches, and anytime I divide something by itself, I get 1. Do I need to write times 1?
No.
Nah. So we essentially would just say they cancel if they have matching powers. Well, here I've got a c to the 5th and a c to the 7th. Well, essentially we could say how many c's cancel away in both cases.
Wait. Well, it would be 1 over c to the second.
Right. These 5 cancel with 5 of the 7, but there's still 2 left right here. So we're left with a c squared. In a sense, we say we subtract the exponents. 7 minus 5 is 2. But the winner was in the bottom, so he stays in the bottom. And then there's Glenn again, with no friends. What do I do with the d, class?
You just put a D
Just leave him where he is. Where is he?
at the bottom.
In the bottom. So where do I leave him?
At the bottom.
In the bottom. If there had been an m right here, where would I leave him?
At the top.
In the top. Don't need to mess with the m, right? Make sense? Let's have you practice some of these things if you would. Page 477 in your textbooks now. Page 477 in your textbooks. I want you to do numbers 2 through 18, the even, in the homework section. Page 477, do numbers 2 through 18, the even, in the homework section. Practicing multiplying and dividing monomials, as well as a little bit of combining like terms.